Okay, thank you. Well, apparently most of the people are getting set for the party tonight, so we are very few. But yeah. So let's start with the introduction to this project. That is a project to port the Ramses code on the GPU. It involves a few people. You see the names here in Switzerland, and is partially supported by the European Commission in the framework of the PRACE project. So a very short introduction about, well, in general, cosmological simulation, in general, and more generally speaking, astrophysical simulation, that are, of course, amazing tools to perform experiments, so the only tools that we have to perform experiments in astrophysics. Of course, you cannot make an experiment to simulate to reproduce the dynamics of a galaxy or a star in laboratory. And so numerical simulations are the only way that we can check and verify the theories and compare to the observation. In particular, one of these code is called to perform astrophysical simulation is called Ramses. It was originally written by Romain Tissier, currently at the University of Zurich. It is a multi-species, multi-phase code that allows to simulate the behavior of different components, dark matter, baryonic matter, stars, photons, and so on, and includes a number of different physical processes, from gravity to MHD, various cooling processes, star formation, and so on. It is an open source code that can be, well, in principle, it could be downloaded, but I've just realized that currently the website is not accessible. They are restructuring all the web domain of the University of Zurich. So at the moment, it's not reachable. The page is not reachable, but in principle, you can download it. It's a full Fortran 90 code. The code size is it's not a huge code. It's like 70,000 lines. It is parallelized both with MPI and OpenMP, but only the MPI version at the moment is public. The OpenMP version has restricted access. So in a nutshell, how Ramses works, you have a time loop. And within this time loop, you have the control, the setup, and the management of the grid structure of the mesh, where you represent, where you describe your physical quantities. Then there are some communication steps. Then gravity, hydrodynamics, and dark matter are solved, are calculated through different techniques. And finally, you can switch on or off different physical processes according to the needs of your study, what you need, what you want to simulate. The main feature, the most important characteristic of Ramses is that it is an adaptive mesh refinement code, which means that the mesh refines only and give you a high resolution only where this is strictly necessary according to the physics of the problem. So this strongly reducing the computational demand, both in terms of memory and in terms of computing time of your simulation. In this talk, and in this work in particular, we will focus on the hydrodynamic solver. The hydrodynamic solver allows you to describe the behavior of the baryonic component of the universe in your simulation. It adopts a fluid dynamics approach, solving the conservation equation of mass, momentum, and energy, and at each time step for each cell, essentially the algorithm is based on the calculation of fluxes, so of the quantity of matter or momentum or energy that is exchanged by the cell that you are updating with its neighborhood through these fluxes. All the hydrodynamics is solved on the adaptive mesh that I was mentioning before. In this case, for Ramses, there are various approaches to implement to enforce the adaptive mesh refinement approach. The one that is used by Ramses is called fully threaded tree, and it has the interesting characteristic. It is a refinement made cell by cell. So you check for every cell of your computational mesh if it needs to be refined. And in that case, it is refined. And besides the physical quantities that are defined on the cell, this cell keep track, store all the links to the parent cell and to possible sons that could have in further refinement steps. So differently from other codes which need a specific tree structure to manage the complex hierarchy of the mesh, in this case, each cell is completely self-contained, and this is a very nice feature from the point of view of the parallel implementation of the code. It's much easier to implement this kind of mesh, to support this kind of mesh in parallel, and from the point of view also of the memory management, because you don't have to define a specific tree structure that is very complex, and it can become dominant in memory. Using some of the memory space that could be dedicated to the physical variables, and so to solve the problem. But at the same time, this AMR structure is also extremely complex from the point of view of the memory management, and I will tell you in a second why. So the first thing is that when you refine a cell, the new cells, the 4 cells, in this case in 2 dimensions, that are generated, the new 4 cells, the new green 4 cells that are generated, are stored in sort of random positions in memory. Then, when you do the same on another part of the domain, then again you store the different, the new cells that you have generated in almost unpredictable, in a sense, part of your domain, and so on and so forth, going on with the refinement. So your cells are distributed in memory in a very complex manner, and this leads to this can lead to strong inefficiency, of course, in memory access, since you have to jump all over the memory while you're collecting the data that you need to update your variables. And this happens when you have, for example, to solve the hydrodynamic problem. This is, for example, the grid at a certain stage of the simulation. So you see that there are grids with higher resolution, grids with lower resolution. What happens in the original, let's say, Ramses code, is that you start identifying the cell that you want, the small chunk of cells that you want to update. You calculate, you get all the information that you need from the neighboring cell that you need to update that cell. Then you solve with the hydrodynamic solver, and then you go back to the, you update the results on the original cell. And you have to do this for, I don't go into the details, but you have to do this for all the cells and for all the different components of your mesh until the mesh is completely updated. Of course, you can already imagine that this for a GPU is a big problem. There are a couple of problems that you can immediately identify with this kind of data structure. First, you have a very frequent, continuous access to memory, which is not the best way to use the GPU. And second, you are integrating only small chunks of small pieces of data, small chunks of data, making let's say, sort of atomic updates that, of course, are not what you want to do on the GPU. So these are problems that on the original code leads to a CPU consumption of about the 33% of the total amount of simulation time. So this hydro step accounts for the 33% of the total time, 22% is the construction, is the exploration, let's say, and collection of data, and 11% is the real solution of the equation. So let's move to the GPU, and let's see how we have faced this problem on the GPU. First of all, let me show you immediately the final result. This is the result. Of course, you don't have to read that, but just notice that the red functions, so this is the output of the Cray path profiler, and you can see that the red functions are the subroutines that are related to the hydro solver. On the left, you see the original code run on the CPU. On the right, you see the corresponding refactored code run on the GPU. You see that all the functions related to the hydrodynamics stuff that have been ported on the GPU have disappeared. So their time, it's not because we are not solving the problem, but of course because they are contributing very little to the total time of the simulation. So already from this image, from this sketch, you see that the porting on the GPU is quite successful, because at least all the contribution from the hydro part are becoming smaller and smaller, have disappeared from this ranking of the most demanding functions of Ramses, comparing the CPU and the GPU. Okay, our target system was already mentioned, so the system where we develop everything, and it's our target system for the simulation, was already mentioned in one of the previous talks, and this Pittsdint machine that at the moment is number 6 in the top 500 ranking, and it's also the number 1 in Europe. And okay, so we are developing everything on this system, and what I want to show you next is how we can get the result that I anticipated a couple of slides ago. So the first step is to prepare the data to move to offload to the GPU. So to prepare to collect all those data level by level. You remember one of the previous slides, the data are distributed randomly in memory. So each level of refinement is distributed in an unpredictable way in the memory. So in order to make an efficient single data copy from the CPU to the GPU, we have to collect all the data of a single level to be stored and send it to the GPU. So the approach that we are following is to pack all the data that we need that belongs to a certain level, and to copy them to the GPU. This has to be done every time step. And unfortunately, due to due to the particular data structure of Ramses, it came out almost impossible to overlap the data transfer with any kind of other computation. So the kind of trick that is usually suggested with this kind of data structure, with this kind of feature of Ramses, is at the moment impossible. Anyway, finally, this kind of process takes just a little more than 1% of the total time of the simulation. So finally, it's an acceptable amount of time. At this point, we have moved the data of a single level of refinement on the GPU. We will do the same for each level of refinement, from the most refined to the coarsest level. And at this point, we have tried to adopt various tricks, various solutions in order to make the GPU implementation efficient. For the first thing is the reorganization, again, a further improvement of the organization of the memory in patches in order to mimic, in a sense, to exploit at best the blocks that each block that is offered by the GPU. So each patch that we are creating will be integrated, will be updated by one of the blocks that you can instance on the GPU. The patches are further grouped in larger chunks in order to increase the occupancy of on the GPU, so to have more and more threads acting and actively integrating the equation. We do all this patch reorganization on the GPU, exploiting the high memory bandwidth that the GPU provides. And so this is also a nice feature that we managed to exploit. All the loops are collapsed, in a sense, are fused in order to improve the performance. And since I forgot to mention the slide for a problem in the presentation is missing, I forgot to mention that everything is done using OpenACC. So we are using the gang and vector OpenACC scheduling processes in order to parallelize all our loops on the GPU. And then, of course, we try to minimize, to optimize the offload, the data copy from and to the GPU as much as possible. So finally, this is what happens. This is the same mesh that we saw previously, and previously in the previous slides, you remember that each cell was moved to the equation solver, solved, and moved back to memory. On the GPU, something different happens. So we try to pack large patches as much as possible in order to have as many data as possible close in memory and let's say sent to the threads, released to and deployed to the threads. At this point, when the patches are ready, so we identify all the patches of a certain level. These patches are grouped together in order to improve the kind of performance and occupancy that you can get. At this point, you move everything. Well, you move a part of the data at that level on the GPU. The GPU solve. Not to the GPU, to the threads. The threads solve the equations and update the cells that are then copied back. The fluxes actually are calculated, are copied back. The cells are updated. All the boundaries are updated, and then you do the same with the other patches, smaller patches at the same level. Then you repeat the same procedure at the coarser level, and then again at the coarser and then again at the cursor level. When you do that on the GPU, you get finally that 33% of the total time that you had on the CPU is reduced to about the 2% of the total time. So on the GPU, we have the Hydro solver. The Hydro solver accounts for the 2%, more or less, 2-3% of the total computing time. So this is of course, a good result. So these are some numbers related, so I don't want to bother too much on the numbers, but just to compare the CPU and the GPU results. So in blue, you see the computing time on the CPU with 1, 2, 4, 8, and 16 cores, while in green there are the corresponding GPU times on, again, 1, 2, 4, 8, and 16 GPUs. So you can compare, for example, the hydrodynamic time for a full simulation. On one core, it's like 56,000 seconds. On 8 cores, so on a CPU, it's like 6,000 seconds. And on a GPU, it's just it is reduced to 3,000 seconds. So we have a speed up of about a factor of 20, a little less than 20 if we compare to a core, and of about a factor of 2 if we compare to a full CPU. Okay, the total computing time, of course, if we move to the total code, the full code, of course, the kind of improvement that you get is not so amazing, is not so large, because of course there are many other parts of the code like gravity, dark matter, so the solution of the dark matter problem that are not on the GPU yet, and so you see that the kind of performance improvement that you get is just the total time minus the time on the GPU is just the total time minus the time, the hydrodynamic time that has, in practice, disappeared. So, yeah, let's move. Okay, here there are other numbers that could be of some interest. The most interesting thing is that if we look at the scalability of the real gravitational solver and the data copy, you see that the hydrodynamic solver is scaling with the processors quite linearly, while the data copy is not scaling as well. We have identified this problem, we have found the cause of this problem, and we are improving this, we are solving, in a sense, this issue. Okay, just to finish, I show you the results in real simulations, so those were sort of benchmarks. You see here a simulation, a full simulation, cosmological simulation starting from base level 7, which means that you have a base mesh, you start from a uniform mesh with 2 to the 8 cells per each dimension, up to a maximum refinement level of 2 to the 16, actually, so 15 plus 1. Here you saw the results very quickly of the simulation. You have that the effective resolution, the effective mesh that you are simulating is a huge mesh, like more than 65,000 cube meshes. This is the effective resolution. And the kind of results that you get out of it is, you see on the top, the scalability, the total time, and its scalability from 1 to 16 cores, and from 1 to 16 GPUs. Of course, well, they both scale quite well. But of course, the 2 times are quite similar because we are considering the total time. But if so, the sum of all the different components in the code. But if we look at Hydro stuff, you see that the GPU is still scaling, and is performing much better than the original code. This is confirmed more or less on a larger, even larger simulation. But yeah, I have no time to go into the details. But still, we have a good performance improvement increase comparing the GPU and the CPU. And okay, this is my final slide. So our objective was to enable Ramses to the GPU. The work is in progress because we adopted an incremental approach, exploiting both Ramses modular architecture and the OpenACC programming model. At the moment, we have ported the Hydro kernel of the GPU, and we are optimizing the final things. We have also some steps in mind, like enabling a cooling function and the radiative transfer module to the GPU, enable the MHD, and move all the MPI stuff on the GPU, most of the MPI stuff on the GPU, so that we can minimize the data transfer. The final challenge will be to enable also the gravitational part that is very tricky for a GPU, and finally, if possible, sooner or later, redesign the data structure, which is the main the thing that limits the possible performance improvement of the code, both on the CPU and on the GPU. Thank you.